Good afternoon, and welcome. Right, so what I'm going to talk about this afternoon is this rather long title, Building a Brain with Raspberry Pi and Zulu Embedded JVM. And really the idea behind this presentation was that, well, one thing, I needed a presentation that would appeal to the audience of Devoxx, because I wanted to get to talk at Devoxx again. But it was more about that I wanted to look at how I could use Java in some slightly more unusual ways. I've been working with Java for a long time. I've been talking about Java for a long time. And certainly in some of my earlier career, I have had the opportunity to do some weird and wonderful things with Java. So I kind of thought, right, I want to continue with doing that. So I came up with the idea of building my own brain. Well, not my own brain, but my own brain that I could use. Right. So, introduction. Where did we kind of come from in terms of getting to the project that I've been working on? I have to say that I've been working on this project for about 6 months now. So it is still a work in progress. I will show you a demonstration at the end, but I liked the line that the previous presenter used, so I'm going to use the same one. Take a deep breath, and then lower your expectations. Like I say, I stole that from the previous presenter. Anyway, inspiration. Inspiration came initially from this book, which is called On Intelligence. And this is a book which was published in 2004, so it's like 13 years old now, so it's actually quite old in terms of technology. It was written by Jeff Hawkins. Anybody heard of Jeff Hawkins? Ooh, one or two people. Anybody heard of the Palm Pilot? Oh, a few more people. Obviously, a slightly younger audience. The Palm Pilot was very popular back in the early 2000s as the sort of de facto personal digital assistant. And one of the things, so Jeff was the co-founder of the Palm Pilot company. One of the sort of interesting things about the Palm Pilot was it had a stylus and you could use handwriting recognition. And the way that it did it was, rather than trying to do handwriting recognition based on any input that people could have, it tried to simplify that in a way that made it easier for the device, which, let's face it, was fairly low power if you think of today's standards, making the handwriting recognition easier from the point of view of the machine. So he came up with what's called graffiti, and graffiti was a way of having a single stroke for each character, and doing it in a specific way so it was easier for the device to actually interpret. So he wrote this book after he'd founded Palm Pilot, where he looked at the way that the human brain works and how that could be taken as a model for building artificial intelligence. And remember, this is 13 years ago, so this is long before machine learning and deep learning became very popular as they have in the last few years. So that was kind of my inspiration. Was I read that book when it first came out, and I thought, this is a really interesting idea. I'd like to do something with that. Clearly, it took me a while to get to it. Now, I will talk a little bit about some things to do with the brain. So we'll talk a little bit about neurology. But I'm not going to spend too long on this because obviously we need to get into the technical side of things. But just as a bit of background, this is a picture of your brain. And the important thing about your brain, from the point of view of the intelligence, is what's called the neocortex. And the neocortex is really sort of the outer wrapper of your brain. And you can see that obviously you've got all these kind of like valleys and dips in the actual brain structure. And the neocortex is wrapped around that. We can see what that really looks like if we take a stack of my business cards. So if you take a stack of business cards, put 6 of them together, what you've got is a fairly accurate representation of the neocortex of your brain. The neocortex consists of 6 layers of cells, so we're talking about neurons, 6 layers of neurons, and they're about the thickness of a business card. So it's a layer of 6 layers of cells wrapped around the outside of your brain, and that's what makes up you, basically. So Jeff did some analysis on this. He looked at the actual mechanics of how these things worked, and he came up with a way of modeling the way that your brain works with the idea that that could be then used to simulate things through a computer and come up with an intelligent system. And what he actually came up with was what he called the hierarchical temporal memory. And this was the idea of a model of how the brain worked. But it's interesting because it takes a slightly different approach to the way that the neural networks that we use today work. Because neural networks today, obviously, you put lots of data in, you train them, they can form connections. Those connections can have certain weightings associated with them that change as the different connections get used more frequently. What Jeff did was to take the same approach, but to also say, well, we'll add time to that. If the inputs don't get used for a certain amount of time, then the weighting decays. So rather than leaving it static and only adding to it when new things come through there, if it isn't used for a while, then the weighting associated with that connection starts to decay, and it's only as it gets reinforced that it will then be built up again. So it was an interesting sort of approach to looking at how learning could actually work by including time as well as all the data input. Okay, so that was kind of the background to where I was coming from. Now let's talk a bit about machine learning. Let's talk about the basics of machine learning. And this particular cartoon's been around for a long time. I remember seeing this when I first started doing computer programming. And if you can't see the exact thing there, what you've got is a couple of ants, and one of them's pointing at a little bit of the flow diagram, which says, then a miracle occurs. And clearly he's saying, we need a bit more detail there. But that, to me, is kind of like machine learning. You've got all this data, and you put it in, and then a miracle occurs, and at the end you get out something which is a sort of decision about what's going on. And it does seem to have this sort of magical quality about it in how it actually works. So let's look at some of the sort of ideas behind this. Learning for computers. So we now have, rather than talking about artificial intelligence, which is a sort of an old way of talking about things, we now talk about machine learning. Marketing's got involved, we've rebranded it, and it's now much more sexy. Machine learning. So the idea here is it's about giving computers the ability to learn without being explicitly programmed. What we want the computer to do is to take input and then learn from that input such that the algorithm or the processing changes based on that input, not based on the algorithm that has been hard-coded into that. It's what the information gives us that changes how the machine works. Now, if we look at the sort of simplest form of this, machine learning, what we're talking about is having a system which needs to be trained. So we have to provide a set of training data that can be used by the program in order to learn how to interpret data that we want to give it at a later time and therefore get results from it. Now, the way that works is that we have what's called labeled data. So labeled data has information that allows us to classify that data. And the way you can look at this is if we look at the kind of simplest example. Simplest example is where we've got a set of data that is two-dimensional. So we have an X and we have a Y. In terms of real machine learning type problems, often you have lots and lots of different dimensions. There are lots of different factors that affect the data, so the different pieces of data that we're dealing with. But if we look at this example here, we've got two axes, X and Y, and the idea is that you've got a set of points on that which are our training data. So we know that if we give an X value for that particular point, we can then get the Y value of that point. And the idea is that we can come up with a function such that if we give it a new X point or a new Y point, we can get it to predict the corresponding X or Y point. Great. And if we look at that as a typical human, we will see that what we've done here is to take that data and draw a line through it such that we have a very simple straight line function that allows us to have what would look like a fairly accurate prediction of the results. Now, you can see that there's one point at the top there which is quite a long way from there. But overall, the error between the line and the results that we've got is fairly low. Now, what you can do in terms of your training data is, ideally, the bigger the set of training data you've got, the more likely you are to be able to train it in such a way that you get better results at the end. But there's also other things you can do in terms of how that training data is used. So rather than just throwing all the training data at the problem and saying, okay, we'll draw a line based on that, what you do is you say, okay, let's take 3/4 of our training data, use that to generate the function, and then we'll use the other quarter of the data to test the function. So we'll make sure that the data works with our training data. And then you can also reorder things, so you can have a sort of sliding window of testing data. So you can iteratively go through and test different sections of your training data and use different sets of data to actually learn. But the idea is that in this case we've come up with a simple XY straight line function. You can obviously become more sophisticated. Mathematics says that we could actually have a polynomial function that we can map to that. So we could actually make the line fit better through our training data and reduce the overall error function between what we've got and the results we have. The problem with that is that you can end up doing what's called overfitting, because with a small set of data like this, we've got maybe a dozen data points. We'd actually come up with a polynomial that would allow us to draw a line that went through all 12 of our training points. Problem with that is that's not a good thing. So even though it actually gives us perfect results for every one of our training points, it's not a good fit in terms of predicting the future. Because again, if we look at that, we'll see that yes, that line goes through all of the 12 points of data. But you will certainly see that if we have an x point which is near to the x-axis, the y-axis, and we try and predict that, we're going to get a very, very large value, even though that doesn't seem like a logical thing from the training data that we've got. So when it comes to machine learning, we need to avoid overfitting based on our training data. And this is one of the things that becomes difficult in terms of judging at what point do you stop trying to fit your data. So the next thing is deep learning. So we talk about machine learning where we have training data that is labeled, we know what the values are, we know what the results are. Deep learning is about taking that a little bit further. So it works with the idea of neural networks. We'll talk a little bit more about neural network nodes in a moment. But the idea of the neural network node is that it takes a set of weighted inputs, applies a function to it, and then generates an output. And then you can link these things together, and you can do that in layers. So this maps to the idea that we have in terms of the neocortex, having 6 layers. You can organize those as layers. You can have non-linear processing, so you don't need to have the same number of nodes in each layer. You can have different connections, things like that. And the idea of this is to have input and then have different abstractions of the problem as you go through the layers. What I mean by that is you could take something like a picture, a photograph, and you can divide that up into, obviously, pixels. So your input is going to be an array of pixels, different colors. You provide that to your input layer. The input layer then has to do something to that and provide an abstraction of the input data. And that could be something like doing edge detection. So you have an abstraction which goes from being a simple set of pixels into a set of edges. And then you pass that to the next layer. The next layer says, okay, those set of edges can then be mapped into starting to recognize an object and classify that as something in the photograph. And then you push that to the next layer and so on. Until at the end of that, you get the output, which is a classification in terms of what is in that picture, whether it's a cat, whether it's a dog, whether it's a person. So you get that abstraction from a set of pixels all the way through into a classification of what's in the picture. This deep learning idea is a good analogy in terms of the hierarchical temporal memory model, because it works in the same basic way, and then you can apply the temporal aspect of it to that. Key thing here is that you use unsupervised learning. So it's data which doesn't necessarily have, won't have labels. It's actually very easy to get unlabeled data. It's a lot harder to get labeled data, because if you think of, if you want to take all the photographs from Instagram, most of them don't have information about what's actually in that picture. So what you really need for recognizing images is labeled data so that you've got an idea of classification. With deep learning, it's more about trying to find patterns in data without necessarily having a classification. So you're looking for where there might be a pattern which you wouldn't recognize straight away. Cancer analysis is a very good example of this, because you may not have an ideal sort of thing about what the cancer is, but the algorithm can spot patterns. And if you then say, okay, well, this person developed cancer, you've got these patterns that can be picked up on, and suddenly you've got information that isn't available or isn't immediately obvious when you look at the data overall. But by doing pattern recognition and finding patterns through this with unsupervised learning, unlabeled data, it allows you to have the system learn about how to predict whether a person will develop cancer or not. Neural network elements. So I said the idea of a node. So the idea of a node is that we have something which represents a neuron. And the neuron has a number of inputs. So we link it to other neurons in our system. Those neurons will provide input to our neuron. That value will then be passed through a weighting function. The weighting function basically says how important is this input. If something has been used many times, it becomes more important. If it's been used less times, it's less important. So the weighting function will adjust the input value based on how important the connection is from that other neuron. All those things are then passed into a function. Function could be a very simple one, like just adding them up. It could be taking the average. It could be doing something much more complicated. And then that produces a result. That's then passed on to the next neuron that it's connected to, or it's passed on as a result that we can then gather together. By putting these things into layers, we can make connections between the different neurons. So we start at the bottom, we've got our input layer. This is where we might pass the pixels from our photograph. We then pass those to hidden layers, and we make connections between the neurons in the input layer and the neurons in the hidden layer. That does some abstraction in the problem, decides where the edges are maybe, or what the type of object is, and passes that on to the next layer. And the next layer is the output layer, and eventually we'll get a result from that. Now, in terms of the way that this is organized, the connections in this particular case are always one way. So we go from the input to the output. There's no connections going back. You can have neural networks where you have what's called back propagation, but in this case we're only doing forward propagation of the results. The other thing is that you don't have connections between the neurons in the same layer. So you only connect between neurons in different layers. Right, so I talked a little bit about deep learning and the idea that what we're doing is using unsupervised learning. The other thing about that is that we typically have more than 2 layers in our neural network for this. And as I say, not necessary to have training data, although not necessarily have labeled training data. The other thing which is kind of an extension of that is reinforcement learning, deep reinforcement learning. And the idea here is that there is no training data. So you don't have a set of data to start off with to allow you to then predict what's going to happen in the future. This is much more like we are as humans. So when you're born, nobody provides you with a nice set of training data which says, right, load all this into your brain and suddenly you're a fully working, fully developed human being. You have to learn. You have to go to school, you have to repeat things, you have to make mistakes, you have to learn from, well, hopefully learn from those mistakes. So reinforcement learning is the idea of doing that with your neural network. So you learn by experience, you have trial and error. You try something, it works, great. You have reinforcement to say, next time we'll do that. If it doesn't work, next time you don't do that. And so it's a way of making decisions based on that. Linked to that is what's called a Markov decision process. Now, Markov decision process, we won't get into too much detail about this, but essentially it's a mathematical model of how you can decide what to do next. And the outcome of what to do next is partly random, but also partly controlled by what's happened in the past. So the reinforcement idea. But there is a certain random element in there to enable things to change. So if you do get stuck in a situation, it will change things so that you won't necessarily get stuck there. What you have in a Markov decision process is a 5-tuple, a 5-value set. So what you've got is a state. Now the state is where you are at that particular time. And you then have an action associated with that state. And that's the idea that by doing something, you're going to move to a new state. There's a probability associated with that. So that it says, if you take this action, the probability that you will get to this state is so much, or the probability you get to a different state is this much. Then there's a reward. A reward's the idea of what is the gain, if you like, in moving to a new state. And this is the idea of thinking about learning by experience. You need to understand, is something going to work or is something going to fail? The only way you know whether it works or fails is based on a reward. So working means something is good, failing is something is bad. So there has to be some feedback in terms of whether it was good or whether it was bad. And then you've also got a discount factor involved there, which is a way of sort of factoring in an importance based on future and present rewards. And again, this is sort of interesting to sort of model with humans. My son really doesn't get the concept of delayed gratification at the moment. He wants everything right now. So he doesn't understand that he has to save up his pocket money to get something in the future. So it's that kind of thing. So you can have a discount factor which can say, okay, well, it's actually better to wait longer for a bigger reward than it is to have a smaller reward right now, that kind of thing. If we draw the Markov decision process as a sort of flow diagram, we get something like this. So the green circles are the different states that we have. We then have a set of actions associated with that, and those actions have probabilities. So if you look at S0 and you take action 0, there's a 50-50 probability that it's either going to come back to state 0 or it's going to go to state 2. And if you look at other ones, A1, there's a 100% probability that taking action 1 will move you to state 2. Then you've got these little squiggly lines, which are the sort of exits, so they're the rewards that you get as you leave from making particular decisions. Now, again, coming back to sort of how I came up with my project, there was an interesting thing that was done fairly recently, and this was DeepMind, a company based in London that got acquired by Google. And what DeepMind did was they looked at how to use what's called a deep queue network. And what this does is allow something to learn and do it in a deep learning way, which means that you don't have training data that's classified. What they did was they basically got their artificial intelligence machine learning system to play Atari games. The great thing about Atari games, in this case, are that they're nice low resolution. So you've got two-dimensional data. It's not a sort of three-dimensional game. It's two-dimensional, fairly low resolution, so a smallish number of pixels. And what they gave the system was the video frames. So they gave the video frames. They also gave it a little bit more information in terms of, okay, they would, from a reward perspective, they would give the system the score that it got. So it didn't have to read the score off the screen. It could actually be given the score as the rewards. And clearly it gave the system the way to control the game in terms of the different keystrokes or whatever to move the paddle. So in this case, you got breakout. And the great thing about this was that the system actually learnt how to play the game without having any knowledge of the game. So no pre-configured knowledge of the game. It simply started doing things at random, started to see which things worked and which things didn't, based on how high the score was. And it learned from that so that it did the right things over time, and it started to learn, okay, if I move the paddle to where the ball is going, I get a higher score. If I don't move the paddle to where the ball is going, I lose, so I'd get a lower score. And that, to me, was a really interesting sort of approach. So I thought, right, what can I do based on that? So the next thing I thought, right, I need some hardware for my project. And for this, I thought I was going to use embedded hardware, so the Raspberry Pi, because what I wanted to do as well was to kind of include a number of different things in the project, hence the use of the Raspberry Pi. So who's got a Raspberry Pi? Ah, yes, great. So you're all fairly familiar with the idea of the Raspberry Pi. Raspberry Pi, fantastically successful embedded development board. Cheap, powerful, great connectivity. The original boards were $25. I guess you could still get the $25 Raspberry Pi Model B, I guess it is. But they also came out more recently with the Raspberry Pi Zero, and that's $5. So it's just incredible to think that this is a fully configured computer for $5. And it's not even that sort of low-powered, even by today's standard. This was launched like sort of 5 years ago, and again, fantastically successful. They actually, there are two companies that sell these in the UK. One is RS, used to be called Radio Spares originally, but now it's called RS, and the other is Farnell. And both of those websites were actually brought to their knees on the day when these were released because they couldn't cope with the number of orders. And they reckon that even since last year, they've sold over 10 million of these boards, which is an incredible feat. If you look at the actual sort of configuration of the Raspberry Pi boards, it's all ARM-based. The older ones are ARM v6, the newer ones are ARM v7, even ARM v8 on some of the newer Model Bs. Pi Zero is still ARM v6, but it does clock at 1 gigahertz. Some of the speeds vary. You can actually change those if you want. The newer Model B actually has a quad-core processor. The other ones have a single-core processor, and you get somewhere between half a gigabyte and 1 gigabyte of memory. So it's not a sort of totally non-powered machine. There's quite a lot of processing power there. So I thought, let's see what we can actually do with that processing power in terms of building some sort of machine learning system. So this was my original kind of concept in terms of the architecture. I thought, right, let's use one Raspberry Pi for each layer in the neocortex to model our brain. We'll have a set of neurons in there. We'll create a neural network between the different Raspberry Pi boards, and then we'll communicate between the boards over a network, have my laptop connected to the network, and then get it to do something. So this was my Mark I Raspberry Pi cluster. What I did was I basically took a bunch of the Raspberry Pi boards that I had, and I kind of bolted them into a stack, found a nice little power supply that had some short USB leads, stuck one on the top to be the sort of like main controller of the whole cluster. In the picture there, you can see I actually added an SSD because I thought I'd need some more storage, and this is kind of what I came up with. I then decided, okay, let's see if I can make this a little bit smaller, and I came up with what I've got here, which is my Raspberry Pi Cluster Mark II. And this makes use of the Pi Zeros rather than the Raspberry Pi Model A or Model B. Again, in this particular picture, I've got hard drive underneath the Raspberry Pi cluster, which I don't use at the moment, because it turns out I didn't actually need that much storage, so I didn't need the extra disk, so I didn't bother including it. Now, what this uses is a nice little board, the red board there that you can see, which is called a cluster hat. All the boards that you stick on top of a Raspberry Pi are apparently called hats, and this is the cluster hat. The way that this works is that the Raspberry Pi Zeros actually plug into the cluster board through the USB connector. So you don't have to, it does networking, it does the connections, everything through the USB, rather than having to have either using wireless or using physical network connections. So it makes the wiring a lot simpler as well. And like I say, basically you've got 4 USB ports there. You can plug 4 Pi Zeros in, and then you use GPIO pins as well to connect and control various things. So it makes actually setting things up very simple. So the next thing was, okay, I want to write this application, whatever it's going to be. I want to use Java. I want to use Java for an embedded application. Right, so why would we use Java? Well, first thing is, write once, run anywhere, or as some people refer to it, write once, test everywhere. Write once anywhere, write once, run anywhere is great because it means that you can develop your code on the laptop, then all you have to do is move the jar file to the device, and no cross-compilation, no tool chain, no complicated things in there. It's just compile your Java code into bytecodes, move it onto the new platform, off you go. So it made life simple in that point of view. Next thing was lots of libraries, lots of frameworks available, so you don't have to write everything from scratch. There's all sorts of nice libraries. We'll talk about a couple of those in a minute. But lots of things that you can use to help you build your application more quickly. For the point of view of the Raspberry Pi, simple interfacing. Again, there's libraries for this. There's Pi4J, there's DIO, which allow you to control things like the GPIO pins, I2C, UART, stuff like that. I haven't actually used those in my demo yet. I've got some sort of ideas for doing things like that, but I haven't quite got to that point in the project. The other great thing about Java is simple concurrency. Because in something like this, what you want is lots of threads doing lots of different things for your different neurons. And having all that coordinated and creating new threads is actually very, very easy in Java, as we know. If you look at Java SE5, there were the concurrency utilities, you've got the things like semaphore, you've got things like read-write locks, atomic operations, things like that. Java SE7, we got the fork join framework. Take a big task, decompose it into smaller tasks, have the framework deal with all of that for you. Java 8, we got the parallel stream. So there's lots of things in Java that make doing things concurrently a lot easier. And then if you do need to kind of delve down into lower level code, you've got JNI available so you can interface with native libraries. If you want to use things like OpenCV, there's a Java wrapper for that that's using things like JNI. My one marketing slide, I do work for Azul, so I will mention that we have a version of Java which runs on ARM. Great, so that's what I'm using for this. What we do is we basically take OpenJDK, we compile it into, in this case, an ARM binary. We support v6, v7, v8, soft and hard float. 64-bit is actually released now. I should change that. It's not close to release. It is released. And we're doing some interesting things around C1 and C2 JIT compilers to improve that. You can download that for free from our website. If you want support for it, we will quite happily sell that to you. Nice thing about this is there's no field of use restriction. It's an open JDK binary, so it's released under GPL v2 with class path exception, so there's no issue of licensing with this. Like I say, download it for free from our website. Right, let's switch back to machine learning, talk about machine learning in Java. So what I did was I looked around and I found that there's this nice library that's been created specifically for deep learning in Java. It's called DeepLearning4J. So what this is all about is creating neural networks, being able to set them up, being able to train them, being able to deploy them into whichever development environment you've got. And really the kind of key part of this is what's called ND4J, and this is n-dimensional arrays for Java. A lot of what you do with machine learning and deep learning is matrix manipulation, matrix multiplication, because when we looked at the graph, we had 2 dimensions. So that was 2 values for each piece of data. But as I said, often you have many values, many dimensions for the data that you're using. So you create a vector of those values, and then what you need to be able to do is, in order to do the neural network, is you need to do matrix multiplication, matrix manipulation. So ND4J gives you that sort of core piece, which does a lot of the mathematics underneath in a much more easy way. The other thing they've got is a thing called DataVec, and this is about transforming the data into those vectors. So you've got the data that comes in, let's say we're taking our image again, so we've got our RGB values for our pixels. DataVec will help you transform that into a set of vectors, which you can then use ND4J to manipulate in your neural network. Arbiter is a way of evaluating how your model is working and then apply more tuning to it based on how well it's working. Hyperparameters are the values that get created, so they're not your data, they're the values that get created from your data. So things like the weighting that you have on your different nodes in your neural network and so on. In terms of classes that you get for DL4J, there's the obvious things. So you've got a neural net configuration. That comes with an optimization algorithm. There's then a multi-layer configuration, because you need several layers in your neural network. This will allow for back propagation. So if you do want to have feedback from lower layers in your neural network, then you can do that through back propagation. And then there's this wonderful TBPTT, forward length and backward length. And I actually had to put that there because it's truncated back propagation through time. So it's really how you tune the way that things work in terms of the neural network. And then obviously you have a layer, you can have dense layers, you can have output layers, and you can have input and output between those layers. So it gives you a basic set of classes that you can use to construct your neural network. You can use the neurons, have them organized in whatever way makes sense for your application. Then there's this thing called RL4J. So this is reinforcement learning for Java. And this was what I particularly wanted to use because the application, as we'll see, is going to use this. So this deals with both low-dimensional state and high-dimensional state. And the idea here is low-dimensional is state-like data. If you've got something in your application where you've got a small number of values associated with it, like a position. So you've got an X, Y, maybe a Z position in your application. That's low-dimensional. High-dimensional is where you've got lots and lots of values. Say a video frame, which has potentially thousands of pixels in each frame, then that's high-dimensional information. We talked about the Markov decision process, so there's libraries or classes in the RL4J which allows you to model that. Also, the deep Q network can be modeled through that. And then you've got various policies that you can apply to how to decide what to do next. If you're in your Markov decision process and you're in a particular state and you need to decide what to do next, then there's various policies that are associated with that. I won't go through them, but there's apt critic, there's a Boltzmann probability distribution, there's DQM policy, and then there's epsilon greedy partially random. So different ways that you can approach making a decision. Right, Minecraft and Project Malmo. Who's played Minecraft? Right, most people. Great. So Minecraft is an immensely popular construction game. I know that because there's literally millions of people that play this game, and lots of them are children. My son, who's 11, is one of them. He loves Minecraft. He loves building things in Minecraft. The thing that really kind of weirds me out, though, is he also is very much like the average 11-year-old child. If you've got children, you're going to know what I'm going to say, which is he likes to watch other people playing video games on YouTube. I really don't figure out why there's so much attraction to watching somebody else play a game when you could play it yourself. But anyway, so Minecraft, very, very popular. There's different modes in terms of how you can do it. So you can do it in creative mode, where you don't ever die. You can do it in survival mode, where you can die, and you can do it in hardcore mode, where you die more easily. The first PC version was written in Java. It is probably, certainly the most successful ever desktop application written in Java, I think. And so, it's very popular. 121 million copies sold worldwide. Mojang, who were the company who first created Minecraft, Notch, the programmer who really started it all off, was acquired by Microsoft back in 2014. Right, so here's a couple of pictures of Minecraft. I don't really need to show that because you all know what Minecraft is. Project Malmo. Project Malmo is interesting because this was a project that came out of Microsoft Labs. And what they did was they looked at Minecraft and they said, actually, this could be a really good thing to use to test machine learning algorithms because it's three-dimensional, but it's a relatively low-resolution 3 dimensions, isn't it? I mean, it's nice chunky graphics, nice big blocks, which means that you're not having to deal with too much in terms of interpreting the data. It's not like trying to play, Tour of Duty or something like that, where you've got very, very high resolution, very, very high frame rates. With this, it's a kind of lesser amount of data, so that kind of thing could be interesting. So what they did was they actually created their own mod for Minecraft, which would allow you to take your machine learning algorithm and kind of plug it into Minecraft so that it could play the game, and then it could figure out what was going on and it could get information about the game. You didn't need to do things like screen scraping, you didn't need to do things like keyboard simulation or anything like that. They provided all the APIs for that. So if we look at a very simple piece of code using Malmo, what you do is you create yourself an agent host, and then you need a client, so it's called a client pool, and that connects to the game. And the nice thing here is that you can actually connect to a game on a different machine. So you basically go across the network, give an IP address, and you can play the game, which is good because I obviously wanted my Raspberry Pi brain to play the game, so that's connected to my laptop and can play the game on my laptop. You then have a mission specification, and the mission specification is where you can set up what it is you want the machine learning algorithm to actually achieve in the game. So there's various things you can set up about that. One is you can say how long you want the game to run for. You can set up the video resolution, things like that. And then you can also record all the information about what actually happens during the playing of the game. This is obviously very good because if you want to analyze how your machine learning algorithm worked in terms of the game, you've got all the details about what happened whilst the game was being played. What you can save is things like what commands we used. You can save the video. You can save the rewards, because you get rewards as you play through the game in terms of what actually happened, and also observations. And then what you do is you simply say, okay, start your mission. When you interact with the game from the point of view of the machine learning side of things, you've got the mission specification. You can do things like setting this allows you to set up the world that you're going to play in. So you can set the mode to creative if you want. You can also do things like adding blocks into the game. So you can set up a specific arrangement of things in order to have an environment that you want to work through. We'll see that when we show the demo. And then you've got the agent host, which is how you control things. You say start mission. You can peek at the world state. And the world state gives you information about what blocks are immediately around you, so you get information about that. And then you've got send command, which allows you to actually say, right, I want to move in this direction, I want to turn in this direction, maybe use a particular block, or whatever you want to do in the game is controlled through send command. So in terms of putting it all together, what I did was come up with a slightly more detailed architecture. So I used Raspberry Pi 3 as the main board, which had the connection to the laptop. And this runs the demo controller, and it runs the Malmo library. So I had to recompile the Malmo library for ARM. That was actually pleasantly simple. Didn't have any real issues with that. There were a couple of minor things I had to tweak, I think, in the build script. But overall, very simple to move the Malmo library from a PC to the Raspberry Pi. That way it can communicate with the laptop in order to play the game. Then we use the Pi zeros as the 4 layers in our neocortex. Obviously there should be 6, but the Pi hat only has 4, so I thought we'll use 4. The way that works is that one of them is the input. Obviously that's running the reinforcement learning Java. That then passes the information from the input down through into filter 1, down into filter 2, into the output, and then what you get back is what to do next. So it's the decision that's been made about what is the next thing to do. Use the Markov decision process and say, okay, we've processed the information we got from our current state of the game, we've made a decision about what to do next, have the game do that, and then repeat by taking the information back and going on. So I needed a demo scenario. So I thought to myself, right, what do I want my machine learning algorithm to do in Minecraft? So I thought, right, we'll have the machine learning algorithm build a house. Great. Yeah, turns out that's really hard. So yeah, I don't think we'll do that because it really is hard. So then I thought, right, demo revision 1. Okay, let's keep things simple. Let's have the agent build a wall. Yeah, turns out that's really hard as well. So simpler, but not as much. So building a house, right. So then I came up with demo revision 2, which is have the agent walk around without dying. So that seemed like a simpler thing to do. It's still not totally simple, but it is much easier in terms of the coding that you need to do. So the idea was that you would create a world in which the agent could move around, and you would put certain obstacles in its way that could potentially kill it. And the idea is then it can move around the world, and if it bumps into something that kills it, it learns that that's not a good thing to do. So the next time that it goes through, it should then avoid the things that kill it, and gradually it will be able to move through the world staying alive. Okay. Applying machine learning to Minecraft, basically, as I said, we're using DL4J, RL4J. That uses vectors. So the tricky bit is taking your problem space, which is playing Minecraft, and translating that into the machine learning side of things, which is a number of numeric values that you want in your vector, which are then going to form the inputs to your nodes in your neural network and have them processed. So to start with, I've kept it very simple, and I'm just using the state information that the game gives me about what blocks are in front of me and around me in order to make decisions. The long-term goal is to go more down the sort of deep queue network idea of taking video frames and having those video frames interpreted to get information directly from those and figure out what's going on. Start with random moves, so it has to do something. It was interesting. I was talking to somebody about this. Oh my gosh, 6.5 minutes. I was talking to somebody about this when I did this presentation at the weekend, and somebody said, "Well, wouldn't the system just learn that if it didn't move, it wouldn't die?" And I said, "Yeah, well, it could do. I mean, that would be a legitimate way to stay alive, is not move. But obviously, in order for it to learn." To start off with, we give it a random way of moving around, so it does move and it bumps into things, and then it should hopefully learn from that. Right, so conclusions, future directions. Conclusions. Right, so embedded hardware can be used for AI, machine learning, deep learning. I mean, I've found that the processing power on these boards for what I'm doing at the moment is quite adequate. You can certainly run a neural network on these boards. We're not talking about millions of neurons, but we are talking about hundreds of neurons. It's not a problem. Cheap to build, multi-core potentially, as might move up into using more of the bigger Raspberry Pi boards for more cores. Java is very much the ideal language for this. Easy to learn, the threading model is easy, lots of useful libraries, like I say, like the RL4J, things like that. And I definitely think that Minecraft is a fun tool for testing this kind of thing. Things I'm thinking about in the future, obviously more work on my Minecraft player, making it into a better player, trying to figure out to get it to do more things than just move around without dying. I'm also interested in experimenting with what's called JCUDA. JCUDA is where you can use GPUs to add processing power. And I've actually got, there's an NVIDIA development board that you can get called the Jetson TK1. It's essentially a graphics card processor where it gives you access to all the GPUs so that you can use those to work as your neurons. Because the neurons, remember, are not really doing fantastically complex processing. So a GPU is actually very well suited to that kind of thing. And it could be interesting to explore using that. And then machine vision, I've also, thinking about whether OpenCV could be an interesting thing for taking the video frames and then doing interpretation on that and figuring out what's going on in the game. Place to go for more information, obviously raspberrypi.org, clusterhat.com is the place where I got my cluster board from, DeepLearning4J.org, Minecraft.net, and Project Malmo. There's if you search on Project Malmo, you find it. Zulu.org is where we publish our binaries for the embedded JVM. As I say, it's free, download it. And with that, what we're going to do is we are going to switch to the demo. Right. So as I say, this is a work in progress. So, right. So basically what I've done is I've got it set up so, yeah, you can see that you've got the Minecraft screen there. What I'm going to do is I'm going to run the application, which then runs on my laptop, uses the Raspberry Pi brain to do things, and then hopefully it will start playing the game. So what we should see is, yeah, there we go, and then it starts moving. So what we're doing is moving, see, it died. Actually, that's, well, yeah, so what it's doing is it's moving through the environment, and I've given it a completely flat environment, and then what I've done is put lava blocks randomly on the flat environment. And so if we go to here, let's go back to the title screen. Here we go. Yeah, go back to the title screen. Yeah, that's right. And if I run it again, like I say, it is still... Then we'll build the terrain, and then it should start moving. Yeah, there we go. So it'll move around. It's kind of as I say, it's using a lot of randomness, and sometimes it just walks off in the opposite direction. Like, yeah, maybe it's going to. Ooh. Oh. Seems to be doing better this time. Yes. No. Ooh. It won't run forever. I've got 4 seconds left. Ooh, we're going to survive, we're going to survive. Yes! Okay, so there you go, it survived. So like I say, that's it. Hopefully that's been interesting. I am planning to put this code up on GitHub when I've tidied it up and actually got a bit more of the stuff going. But I will put the code up on GitHub. So with that, thank you very much.